Let's take a look at the simple machine known as a lever. As a bit of a review, one of the reasons we use simple machines is to gain mechanical advantage. Mechanical advantage is the number of times a machine multiplies your effort force. 1 is the magic number. If the mechanical advantage is greater than 1, that means that your effort force was less than your resistance force. But the trade-off again is that the effort distance is longer. If you have a mechanical advantage less than 1, that means your effort force was greater than your resistance force. And then again, the trade-off is your effort distance is smaller. It's important to know that mechanical advantage can never be less than or equal to 0. Ideal mechanical advantage is your theory-based calculation based on how the machine was built. What we do is we focus only on the distances. So your ideal mechanical advantage is the ratio of the distance traveled by your effort force over the distance traveled by your resistance force. Once you have your ideal mechanical advantage calculated, you can also figure out your ideal effort force. Your ideal effort force is simply found by using your ideal mechanical advantage, putting the force of your load on top, and then the force of your efforts on bottom. So by solving for F sub E, you would find your theoretical force needed to lift that load using this particular lever. The actual mechanical advantage is something you get when you actually try out your simple machine. The actual mechanical advantage is simply a ratio of the force of your resistance to the force of the effort that you are applying. Okay, so let's start taking a look at your actual levers. By definition, a lever is just a rigid bar used to exert a pressure or sustain a weight at one point of its length by the application of a force at a second and turning at a third on a fulcrum. So here you can see we've got 3 different pictures of levers in action. We're going to take each one and look at each one individually. A first-class lever is defined as the fulcrum located between the effort and the resistance force. If you look at all of those pictures on the bottom, you can see the fulcrum is in the middle. The effort force is indicated by that yellowish-green arrow. The resistance is your blue arrow. No matter what, though, the fulcrum is in the middle. The effort and the resistance forces are applied to the lever arm in the same direction. So if you imagine, an example would be like a seesaw. So each person is sitting on the ends, and they're both pushing downwards. First-class lever is the only class of lever that could have a mechanical advantage greater than or less than 1. And you can see, just looking at the pictures, if the distance from the resistance to the fulcrum is equal to the distance from the fulcrum to the effort, you're getting a mechanical advantage greater than 1. If the effort distance to the fulcrum is less than the resistance distance to the fulcrum, your mechanical advantage is less than 1. If, however, your resistance to the fulcrum is lower than your fulcrum to the effort, your mechanical advantage will be greater than 1. With a second-class lever, the fulcrum is located at one end of the lever. Then the resistance force is located between the fulcrum and the effort force. The resistance and the effort force are in opposing directions. A second-class lever will always have a mechanical advantage greater than 1, again, because the distance from the effort to the fulcrum is greater than the resistance to the fulcrum. No matter where this resistance goes along the lever, since the effort's on the end, that distance will always be greater. With a third-class lever, the fulcrum is located at one end of the lever, the effort is located between the fulcrum and the resistance force and the effort force are in opposing directions. A third-class lever is always going to have a mechanical advantage less than 1 because the distance from the effort to the fulcrum is smaller than the distance from the resistance to the fulcrum. Let's take a look at some of the math associated with levers. Before we do that, we do need to define a couple more terms. So take a look at a lever's ideal mechanical advantage. Okay, so this would be a type 1 lever because the fulcrum's in the middle and the effort and the resistance are on the edge. If I want to define that ideal mechanical advantage, it's the distance from the effort to the fulcrum over the distance from the resistance to the fulcrum. If I were to just apply the effort force, if there was no resistance, the effort would just cause the lever to pivot in a circle. The same token, if there was no effort force, the resistance would just cause this lever to rotate clockwise around the fulcrum. The tendency of an object to rotate around a point is called a moment of force. We usually just call it a moment. It's the tendency of a force to twist or rotate an object. So this greenish arrow, again, would cause it to go counterclockwise if unopposed. Your resistance would cause it to go clockwise if it was unopposed. The moment is equal to the force applied, so the strength of either the effort or the load, and the distance it is from the fulcrum. Let's take a look at this first class lever and put some numbers with it. Okay, so we want to only apply a 15-pound effort force, and we know that we're 5.5 inches away from the fulcrum. If I want to figure out the effort moment, so again, that's the tendency to rotate around a point, I'm going to take my force times my distance. 15 pounds times 5.5 inches gives me a value of 82.5 inches times pounds. All this is it's a tendency to rotate around an object. The bigger this number, the more likely something is to rotate around the fulcrum. The smaller this number, the less likely it is to rotate around the fulcrum. When the effort and the resistance moments are equal, the lever is in static equilibrium. Static equilibrium is just a condition where there are no net external forces acting on a particle or body, and that body remains at rest or continues at a constant velocity. For our purposes, we're going to focus just on the remains at rest part. So how is that used? What I can do is what's called, again, a lever moment calculation, and I can figure out how far this resistance can be from the fulcrum if I only want to push down with 15 pounds of force. So we're going to use what we know regarding static equilibrium and calculate that unknown distance from the fulcrum to the resistance force. If we're in static equilibrium, the effort moment has to equal the resistance moment. We've already calculated the effort moment. Now I'm going to take my force of the resistance given to me in that diagram, and I want to multiply that by the distance of that load from the fulcrum. For this to be in static equilibrium, that distance only needs to be 2¼ inches away. Once we actually try out this lever, though, we might get a different actual mechanical advantage. Again, the ratio of the applied resistance force to the applied effort force is what gives us our AMA. So let's say it didn't take us 15 pounds to do that, but instead it took us 16 pounds. The actual mechanics of the lever above, we're going to take our force of the resistance, what it is that I'm able to lift, divided by the force of the effort, so what I was putting in. 32 divided by 6 gives me an actual mechanical advantage of 2:1. The ideal mechanical advantage is, again, the ratio of the distances. So it's the effort arm length over the resistance arm length. Plugging in those numbers, our ideal mechanical advantage is 2.44. Okay, notice how these values are not the same. The actual mechanical advantage, again, takes in things like friction or air resistance or any unknown factors. What we can do then is do an efficiency calculation. So it's the ratio of useful energy output to the total energy input, or in other words, the percentage of the work input that's converted to the output. It's simply the actual mechanical advantage over the ideal mechanical advantage. Using the information on the previous slide, our actual mechanical advantage was 2, our ideal mechanical advantage was 2.44, so I'm going to get an efficiency of 82%. That's actually not too bad. No machine is going to be 100% efficient, again, because of things like friction or air resistance or anything else that could cause our machine to not work perfectly. This concludes our lesson on levers. Please ask any questions that you still have.